All right, welcome back. In our last class, we looked at the basic timers 6 and 7, and we looked at how we might use interrupt service routine and connections to NVIC to basically utilize the timers to trigger a GPIO port. In the last class, we connected the blue LED and the green LED that was on the board, and we made them blink or toggle every time we entered a timer 6 interrupt service routine or a timer 7 interrupt service routine. So during that whole scheme in the basic timer, as you recall, here's the architecture of the basic timer we looked at. We had a timer clock that was basically the system clock or the bus clock that's coming in. This trigger out is for ADC and DAC, and we'll talk about them later. But that timer internal clock basically was driving our prescaler. And we saw that by changing the value in the prescaler and the auto reload register, we could basically get the correct timing that we want for our interrupt service routine. Last lecture, we had timer 6 interrupted every 1 second, and timer 7 interrupted every 5 seconds, and we saw how to place the values of the ARR and prescaler based on the original clock frequency here correctly. Now, when the processor is running like this, the timer is a freely running counter. It's counting from 0 to whatever the value might be, the maximum value based on how big of a counter it is, 16-bit counter, 10-bit counter, or in our case, by setting the auto reload register, we basically ask the counter to count up to a certain value. So for instance, if it's a 10-bit counter, normally it'd be counting to 0 to 1023, and then when it hits 1023, it will reset back itself to 0. That's when the update event would happen. Now by setting a auto reload register, as we saw last time, we can change how much the counter counts up to. So auto reload register, as you recall, if you place a value that's smaller than the maximum possible value of the counter will count, and it's shown here in the red ink right here, is it'll start at 0, go up to the value set at the auto reload register, and then count back to 0, and then drop to 0, which will then trigger the interrupt. And we are relying on this update event, these update events, to trigger an interrupt. Okay. Now, during this time, the processor is running, but it gets interrupted. There are other modes that are available within the counter that we have. Besides the basic counters, we have a general purpose counter and an advanced counter. Today we'll look at one of the features of these two styles of counters that are related to driving an output pin. It's called output compare. And then next we'll talk about output compare together with generating a specific type of pulse called a pulse width modulation, okay, PWM. First, let's look at output compare. So what exactly is a counter? And before we go to output compare, let's take a look at the different modes in which the STM32F4 counters can be set up. So far we've talked about an up counter, and then count goes to 1023, it resets back to 0, right? This was an example, 1023 only because here I said the example is for a 10-bit counter. Going up to 1023, resetting to 0, starting count up again, 1023, and so forth. Now, we can have a variety of counters. One such counter is called up counting. So our counters in the STM32F4, especially the general purpose counters, can be set up in one of three modes. An up counting mode, which is the normal mode we've been talking to. So you count up from 0 to either the ARR or the full count of 16-bit, 32-bit, or 24-bit, depending on the particular counter, or up to the ARR value. When you get to the ARR value, you've gone past the boundary you've shown, you've set up for this counter, and then you overflow that boundary. So, and then you overflow that boundary and go from the value of ARR back to 0, right? So that triggers an overflow interrupt. This is the up counting mode. So when you go from the ARR, you reach ARR and reset the counter back to 0 and start the counter again, that is called an overflow. Now, you can have a counter, instead of counting up from 0 to ARR, like we saw on the SysTick timer, we can have a counter that's counting down. So by default, the counter is set up to count up, but we can have the counter mode, the general purpose timers in the STM32F4, the counting mode can be set up to be down counting mode. What that means is you start at a particular value. So you start a value called ARR, or a full range if the ARR is not specified, and then you count down towards 0. Every clock cycle you're counting down by 1. You eventually hit 0. When you go to 0, it's called an underflow, and that triggers an interrupt if you have interrupt set up, or it triggers an underflow flag that you can be read in a polling mode. So when you get to 0, you then reset it or auto reload again to the ARR value, and then you count down again. So that's called a down counting mode. So we've seen so far the up counting mode, down counting mode. There is also another mode. This abruptness of the count going from 0 to the ARR value, or in the previous case, from ARR value down to 0. It's a very abrupt change. If you notice, this is a gentle slope, and the count is changing by 1 all the time, and here we have an abrupt change from ARR to 0. This can be problematic for certain kind of applications. So there is a specific kind of counting mode called the center aligned mode, where instead of counting up or down, you do both. And this is what it looks like. So you start counting at 0 when you start the counter. You get to ARR, and then instead of abruptly jumping down, you count gently down towards 0, and then you count up from 0 up to ARR, so creating this triangle looking waveform. This particular mode is called the center aligned mode. Now in the center aligned mode, you can have an overflow because you've gone past the ARR, and that's why you're heading down. So that's called the overflow, and that can be used to generate an interrupt. And when you get to this bottom point right here, you can have an underflow, just like how you would from a down counting mode. You have an underflow, and then you start counting up again. The advantage of this particular style of counting is that there is less abruptness between the two values at the extreme, okay? And is useful for certain kind of applications like pulse width modulation for power electronics and so forth. Okay, so we'll talk about that later. Okay, so there's 3 different kinds of mode. This mode selection wasn't available in timer 6 and 7, but is available in the general purpose timers and the advanced timers we're going to talk about today. So today I'll randomly pick timer 4. A timer 4 is one of many general purpose timers. There's lots and lots of timers. Timer 4 is a 16-bit timer in the Cortex M4. The nice thing about this is that it has multiple options. And these options allow you to do input capture, which we'll talk about in a different time. Today we'll focus on output compare and then PWM generation later. 4 independent channels. Okay, let me quickly elaborate that. So this was the general block diagram we were working with earlier with a basic timer. What does a basic timer have? Well, a basic timer has nothing more than a way to divide the clock frequency, that's a prescaler, a way to load a value up to which you want to count or count down from, that's an auto reload register, and the combination of the prescaler and the auto reload register basically give you precise control over how quickly you want this update interrupt flag, or the update interrupt flag to come up. So this was the idea behind the basic timer. When you go to the general purpose timers and the advanced timers, this block diagram becomes a little more complicated. So let's take a look. Well, here is one of many general purpose timer block diagram that's available in the Cortex M4. So now let's take a look here. What do we see? Well, if you recall, this part right here from looks familiar. Clock prescaler, the clock counter, driving the counter, update interrupt flag coming out, and then auto reload register as well coming, being loaded into the counter. Well, this part right here looks somewhat familiar because they look like this. So the general purpose counters are basically our basic counters. So if you look at this trace right here, internal clock going through the trigger controller, which we're not using right now, into the prescaler and the counter. They look the same. Except now, if you read the description of the general purpose counter, it says up to 4 independent channels. 16-bit counter with 4 independent channels. What does that mean? Let's take a look. So what that basically means is that there is a way to bring an input of some sort into the and use that input to do certain things related to the counter. And you see there's 1, 2, 3, 4 different ways to bring in the input. So those are called channels. Similarly, if you focus on the output, so we're going to talk mostly about the output today, you see the same deal here. I see timer X channel 1. In this case, X is timer 4 for today's example. We're going to use timer 4. So timer 4 channel 1, timer 4 channel 2, timer 4 channel 3, and timer 4 channel 4. So we see the 4 channels right here. That's what the documentation was referring to when it talks about different channels. Now, connected to each of the channels are specific registers. So a capture, which is related to the input data coming in, a capture, a compare, which is related to the output. Okay, so we have a capture / compare register, and there are 4 of them. So there's 4 registers called a capture compare register, and based on the block arrows you see here, what these block arrows are indicating is that at some point something causes the value that is in the counter. So the block arrows all originate, all 4 of these block arrows, if you look carefully, originate in this freely running counter. So this 16-bit counter, for the purposes of timer 4, basically feeds the capture compare 1 register, the capture compare 2 register, capture compare 3 register, and the capture compare 4 register. So the value of these have something to do here. It can be counter can be loaded here, or there is a way to compare what the current count is together with what we have written to the capture compare register. So that's another way to think about this as well, is that those block arrows are indicating that we can compare between the counter register and the capture compare register. So there are 4 of them. Okay. All right. I'm going to focus mostly on, since we're talking mostly about output control or output capture in this particular case today, not input capture. Let's focus just on the output side of things. So we have one of our clocks, internal clock and high-speed external clock, or an internal trigger of some sort, which comes to the trigger circuit. So that's a trigger circuit right here, simplified as this. Goes into the clock prescaler. So that's a clock prescaler right here. The prescaler clock counter, that's a 16-bit counter with the auto reload register, and that goes into, that can be fed into the capture compare register or can be compared with the capture compare register. So here I say greater than, it can be greater than or equal to. Is count greater than capture compare register 1? Count greater than capture compare register 2, count greater than capture compare register 3, and count greater than capture compare register 4. You could also ask the same questions about whether count is equal to one of these guys. You get to feed values in here directly from outside when we load the program. So we could write values to capture compare register and capture, and this, since this is freely running and this is a value we can set, we can say, hey, when does the counter become equal to this or greater than this? That can in turn be used to drive an output, one of the output pins, and that's what's called channel 1, channel 2, channel 3, channel 4, right? In order to drive an output, we need to think about the GPIO. So if we look at the documentation of GPIO, so GPIO in the reference manual, let's go take a look quickly at the reference manual, chapter 8 of GPIO. So here's a highlight from there. In chapter 8 of the GPIO, it says on the very beginning, right here, let me actually pull up the documentation here. So it says right here, GPIO feature, right at the very beginning, we looked at there was 16 pins per GPIO port. So the GPIO A, B, C, D, E for our STM32F4 100-pin packets. Each of these GPIO pins can be set up as an input and an output, either an input or an output. We did that already. We've been using LEDs and buttons as inputs, outputs, together with the RPG and so forth. We've gotten the hang of that. Additional options for each I/O port is analog function. We can read an analog sensor or write an analog value, so analog input and output. There's yet one more thing called alternate function input output. Okay. So each of these GPIO pins can also be used for an alternate purpose. That is not just a simple input output. An alternate function can be a UART channel, an SPI serial protocol, I2S sound communication protocol. It could be USB on the go. It could be connection to your flash memory, all the data and address registers, address bits connected to your flash memory. So more than just using that as a GPIO, it is being used as a specific functionality. Okay, and under the GPIO functional direction on that chapter, it talks about alternate function push-pull or alternate function open drain or pull up, pull down capability. So in other words, you can have an alternate function towards the input from the input side as well as the output side. If you look at the block diagram of a basic pin, right? So here's the basic structure of a pin. Here's the I/O pin coming in. Pull up, pull down register. You can see this Smith trigger. Well, if you want analog functionality, we don't want the Smith trigger, so here's the analog functionality. You can also use the input coming in from the pin to do some alternate function. Instead of sending data to the input data register, you can set up that pin to be an alternate function input and grab that towards additional internal peripherals or internal registers like UART, SPI, and so forth. Similarly, you can push data from the chip to the pin out, to the output pin, through the alternate function output mode. Instead of the output data register, which we've been writing to, we can use that pin to set up an alternate function output. So alternate function output can be done by setting this multiplexer to a certain value and then basically moving out. Okay. How do you select that multiplexer? Well, let's take a look. On this data sheet here, you can find an alternate function, selecting an alternate function, the STM32F4 or 407. So there's a total of 16 pins labeled 0 through 15. There are two multiplexers that select alternate functions. Alternate function 0 through alternate function 15. So a total of 16 different potential functionality mapping onto every single pin. So think about the blue LED. The blue LED on our board is connected to port D pin 15. Port D pin 15. Okay, well, pin 15. So pin 15 has to do with the second multiplexer right here. Okay, because pin 15, 8 through 15 is connected to the second multiplexer, pin 0 through 7 is connected to the first multiplexer. In order to select the pin 15 alternate function, you need to write to a register called the alternate function register high part. And if you want to connect to pin 0 through 7 for any of the ports, then you write to alternate function register low. Okay, so it's a 32-bit register. Well, what are the different alternate functions? Well, by default, AF0, the system, that's what's being used. If we want to use a timer, so I talked about timer. Well, I specifically talked about timer 4, so that would fall under alternate function 2 right here, AF2. Selecting alternate function 2 using the values in the AFRH register so that can be mapped to the pin out. So in other words, by selecting a particular value in the alternate function register high, we can set the alternate function output through this multiplexer towards the output pin. Okay, what are the different alternate functions? Well, let's take a look. On the discovery manual, you can look at the pin, this table right here, table 7, STM32 pin description versus port functions. Well, list all the ports. So this is saying port A pin 1. So let me zoom in just. Okay, port A pin 1 can be used as USART, USART4 receive, Ethernet clock, Ethernet receive clock, timer 5 channel 2, timer 2 channel 2, or it can be used as an analog port input 1. These are all the various functions that are available on port A1. Well, today we'll let's take a look at the blue LED, because I want to connect and map the blue LED. And in our board, the blue LED is connected to PD15. So let me zoom in there. So PD15, it says PD15, which happens to be the blue LED right here. PD15 blue LED, and this is, by the way, the Discovery Kit manual, not the reference manual. It says PD15 is connected to FSMC. So this would be the flash memory controller, data line 1, D1, that's what it means. Or it can also be connected to timer 4 channel 4, in addition to being used as general purpose input or general purpose output. Right now we're using it as a general purpose output to drive the blue LED, but we can use that also as timer 4 channel 4. Well, what does that mean, timer 4 channel 4? What that basically means is that if we configure port D15, we can have this channel 4 right here, this channel 4 right here, we can have that channel 4 be port D pin 15. On our board, that port D pin 15 is hardwired electrically to a blue LED. So anything we see on the channel 4 a high will come out on that blue LED with a light on. Anything that's low on channel 4 will come out on that blue LED as a logic low. Right? So in other words, timer 4 channel 4 is connected to port D pin 15. So port D pin 15 is right here. So right, this pin right here, and this is the thing that I just highlighted in the reference manual figure. And this is alternate function 2 in the multiplexer that we just talked about. Okay, and this is from the data sheet that we just talked about as well. So we have a way to allow timer 4 channel 4 to show up and be visually represented on the blue LED. Okay, how do we do that? Okay, and that is called output compare. So what we are going to be basically doing is we're going to be allowing this counter to run, and if the counter ever equals the value we set in this register, the register 4, we're going to write a value to this register, and if the counter ever reaches that value, then it will drive this channel 4. How does it drive the channel 4? Well, let's go take a look, and that's called output compare mode. So when we use this timer in its output compare mode, we can control an output pin, either put a logic 1 or put a logic 0, or we toggle its value. Okay, we can toggle its value by setting certain bits. So for example, here it says, when a match is found between the capture compare register and the counter, the output compare function assigns the corresponding output pin. So in our case, timer 4 channel 4 assigns corresponding output pin, which is port D pin 15, to a value defined by the output compare mode. The output compare mode basically allows us to set the pin as always high, meaning set active, set the pin to be inactive, meaning always 0, or we can set it to toggle. So it was high, then it's going to be low. If it was low, it was going to be high. It can also generate a flag for the interrupt if we wanted to do additional things on the interrupt. And then we can do other DMA things. Okay, how do we do all of this? So how do we do output compare? Okay, great. So the overall diagram, what do we need to do? We want to write a value on this value. We want to let this counter run, and we want to compare. Well, in order to let this counter run, we got to first enable the clock, timer 4 clock. We got to enable port D pin 15 because we want to be able to see there. After that, well, we know that the internal clock runs at 16 megahertz. Well, how often do we want this output compare to happen? How often do we want this event to happen? How often do we want to change this freely running counter value? Well, that depends on the prescaler and the ARR register, right? Once that happens, then whatever is in the counter, we can compare using the capture counter register, okay? So now let's go and do that. So if we look at the reference manual on chapter 18, it walks us through the various steps necessary to make this all work. So it says on the procedure, it says select the counter clock. This assumes that you've already enabled the timer. You've already identified the GPIO port that is going to be used as the output, and it assumes that you've already set the alternate function registers for there so that you can use that timer channel to drive that pin. Once that's already been set up, so in other words, if the port has already been set up, how do you make that port active? Well, first you got to say which clock are you using. In our case, this is by default internal, unless we do extra additional work to make it external. We also need to set the prescaler because we're counting down or dividing the original bus clock, APB1, APB2, whatever this timer might be, and dividing it down. We can choose not to divide it, but we might be able to divide it as well, and that's done in the prescaler. Then we want to write the value, a desired value, in the auto reload register. That sets the period. We also want to write a value at the capture compare register. In our case, we want to write it to capture compare register 4 because we want to drive channel 4. For our particular case, we won't do any interrupts. What I want to be able to do is, unlike the last example where we used timer 6 and 7 to drive the blue and the green LED in interrupt, I don't even want the processor involved once the timer is set up. I want it to just be taken care of without the processor having to actively go in interrupt service routine and actively toggle the pin. Instead of doing that, I want to use the built-in hardware to do a hardware toggling of that blue LED. Maybe the same way we did it before with a 1 second toggle rate. Okay, so we're not going to do interrupt. So basically means we set it up to toggle. If I have high, low, so I need to set that to toggle, and then I have to enable the counter and just wait for it to work. All right. Well, let's do just that. Using the output compare, let's turn on the blue LED on and off for half second each. So meaning, if I look at the waveform on the logic analyzer, I should stay high for half a second and low for half a second. Okay, so that's what I want to do. Okay, so what are the steps again? We need to enable the clocks. Blue LED is on port D, so we have to go and enable the RCC AHB1 peripheral clock, and we also need to enable the APB1 ENR, right? So let me go open a Keil project here. Okay, so I have a blank project created. Okay, I have a blank project created, and what I want to do is walk through on how to make this all work. So first thing, well, let's include the necessary include file, which is the STM32F4 blah blah blah. Okay. Next up, what do we want to do? I'm going to basically copy and paste the procedure from right here. So in this manual right here on chapter 18, under output compare, so I'm looking at functional description, okay, and I'm going to look at output compare mode. So this is the procedure I was talking about. Okay, this is the procedure I was talking about. So I'm going to copy and paste, copy, okay, and I'm going to bring it here and paste it right here. Okay, so that we can basically follow this. And let me put a block comment so that I don't get tons of errors here. Okay, like I said, this procedure already assumes that you've set up the proper clocks. Okay, so we'll work with that. All right, so let's define. So I want to define my what is it called, LED blue as being pin 15, right? So PD 15 and timer 4 channel 4. That's LED blue is on 15. So that's just want to know, make sure we have that. Okay. All right. So let me start with the main routine. And at the end of main, I want to do nothing and just hang out in while, and that's it. That's all I want to do. Okay. All right. What is this error about? Expected expression, sure. While 1. Okay. All right. In main, what do we need to do? First step. All right. We need to enable clocks for GPIO D and timer 4. All right. According to my chapter 7, GPIO D is in RCC AHB1 bus. Timer 4 is in RCC APB1 bus. So let's go ahead and enable them. So GPIO D. So RCC B1 ENR, and we want RCC AHB1. my autocomplete is having issues here. GPIO D enable. All right, so we want this. All right, so port D clock has been enabled. RCC APB1 ENR. Well, what are we enabling there? We're enabling timer 4. RCC APB1 ENR on ENR underscore timer 4 enable. Not timer 14, timer 4 enable right here. All right, so enable timer 4 as well. All right, what do we need to do next? Well, next we need to look at the GPIO and set it to alternate function. So let's take a look. In the mode register, we need to set, we've been doing input and output, but we need to set the mode bit of port D pin 15 to 10 so that we can have an alternate function mode. So we need to write this mode bit as 1 and a 0 here. So in other words, mode 15 upper bit should be a 1. That's what we need to do. So let's go do that. So we're going to set alternate function on port PD15. Okay, so how do we do that? GPIOD motor pin motor, and what we want to do is by default under reset this is at 0 for port D. For other ports it says, so I'm going to assume that that's correct. So a GPIO motor mode 15, and the upper bit is what I want to set, 10, right? Okay. Next, I want to go to GPIOD not motor, but AFRH register. So AFR register is high and low. In the GPIO structure, the high and low register is set up as an array of 1 and 0. So 1 refers to a high. Oh, there's an error. It's a marking error because I forgot a semicolon here. So this should be or equal. And let's take a look at the auto AFRH register. So AFRH 15 has 4 bits that we need to set. We want to set timer 4, which happens to be an AF2. So timer 4 is AF2 for port 15. That's why we're pin 15. So that's why we're looking at AFRH in 4 bits. It says to select AF2, we need to write a 0010. So in other words, in the 0th bit, we put a 0. On the first bit, we put a 1. In the second bit, we put a 0. And the third bit, we put a 0. So the first bit of AFRH 15 needs to be set to a 1. Okay, so let's go and set that up. Now, here you can use the same kind of notation here for the GPIO AFRH AFRH 15. All right, 15 is not available. Let's go find out. How high does this go? 7. We want the 0th first. We want the first bit to be set as 1, and I'm going to look up the mask for this right now. Okay, so we want the 0th, the first bit to be set as a 1. So let's go see the mask. Here, right click, go to definition of that. It says AFRH 7 underscore 1 is, I see what they did. AF select 15-1. All right, let's see. So this bit right here, there's only 1, 2, 3, 4, 5, 6, 7, 8 different AFRH values possible in the high register. So they basically call it 7 underscore 1 instead of 15 underscore 1. Okay. Another way to just write this, if you don't want to deal with this kind of thing, is to just say push 1. How many positions am I pushing? I am writing a 1 on bit 29. So I could just do 29. Okay, so I can do that as well. All right, I can set that up like that. Okay, I'm just going to use this. So again, what was that again? Right click, go to definition of 7.1, and it says it's select 1. Let's verify that that's what actually is happening. is selected. Yep, 10 by 15 positions. That's perfect. That's exactly what I need. So I can use that AFRS7_1, or I can basically say AFS, I think AFSEL. SEL, yep, SEL 15_1. So that's the first bit that needs to be set high. Okay. At this point, we have the alternate functions all set. Now we can start following that procedure that's mapped here. So it says select the counter. Okay. Before that, let's make sure that we actually set this timer to an output compare mode. And how do you do that? Let's go look. The way we set this up in an output compare mode is in the timer capture compare mode register. There are two registers, mode register 1 and mode register 2. Mode register 1 deals with channel 1 and 2. Mode register 2 deals with channel 3 and 4, because every timer has 4 channels. So we're looking at channel 4, so we want to look at capture compare for selection and put a 0 0 there. So in bit 8 and 9 we want a 0 0 there to set it as an output. When the processor is reset, it defaults to a 0 0. But if you wanted to, you could rely on the reset to make it an output by default. But since this is the first time we're doing it, I don't want to forget it, so I'm going to say set CC4 channel to output mode. That's a default after reset. I'm going to just set it anyway. And how do you do it? It's very easy. Timer for the register is called CC mode register 2. And what are we doing? We're clearing the bits. And what bits are we clearing? And equals not TIM CCMR2, and it was called CC4S. CC4S. Right? And the mask for the CC4S is 1 1. So not at 0 0, and it together, and it clears it. Okay, so we've done that. Next, we want to set the clock. Okay, what clock do we want to set? We have a 16 megahertz clock coming through. So timer 4 prescaler, let's make it easy. So we want it to blink at half a second high, half a second low. So let's bring the 16 megahertz clock, because that's a big clock, to some reasonable value. And here's a quick way I wanted to show you how you might be able to do. 16 megahertz is 16 followed by 6 zeros. 1, 2, 3, 4, 5, 6. Okay. Let's say I wanted to bring the clock output that's driving the counter, which is basically the prescaler clock, to 1 kilohertz. In that case, the value I want to put in the prescaler is 16 million divided by 1000. This whole thing minus 1. That's the value I want in my prescaler. So this value basically guarantees that the prescaler divides the 16 megahertz clock, so it is running the counter at 1 kilohertz. Okay, all right, you can do that. If you think this is too much math, for unnecessary math for the processor to do, divide by 1000 is fairly easy. So you can get rid of 3 zeros and basically call it 16,000 minus 1, or you can call it 15,999 can be written to the prescaler. So what that means is right at the prescaler, now the clock is 1 kilohertz. Right? 1 kilohertz. If I want my thing to be on for half a second and off for a half a second, I want a 2 hertz clock. So that means I want to divide that timer. I want to be able to divide that by a total of 500 to generate the clock I need. So let's see, 500. Okay, so what this will do is now it will create a 2 hertz clock for us. Okay, All right, let's go and take a look. All right, so yep, that should be right. Okay. So, all right, so we're going through the procedure here. We were talking about 16 megahertz clock and generating a 1 kilohertz clock. How do we do that? Prescaler 16 megahertz divided by 1 kilohertz minus 1, so that value gets put in the prescaler. Up counting mode, we want to count from 0 to auto reload. By the way, up counting is by default. 1000 minus 1 is 999. Okay. This would set up a 1 hertz clock, I think, but no, actually this is right. It should be 1000 because we're trying to generate. Let's find out. $999. Okay, how did I get to that number? I want to toggle at the rate of half a second. So toggle. So UI, the time for UI or toggle is 0.5 second. Frequency of that is 1 over the time, so that's 2, right? So ARR needs to be CK count a clock, which is right now how much is 1 kilohertz. That's what we said it would be, divided by the amount of change minus 1. So 499. So it looks like it's 499. So it should be 499. Okay, perfect. All right. Next, we need to, let's go and look at the procedure here. Let's go and take a look at the procedure. The next procedure is we want to write to the capture compare register. Okay. It says in the documentation for the capture compare register, if the capture compare channel is configured as an output by setting the with the help of CC4S bits, the CCR is loaded in the actual compare register. It is loaded permanently. The active capture compare register contains a value to be compared with a counter and signaled on the OC4. Right? CCR4 register can be set to any value that's less than ARR. Okay, any value that's less than ARR, and we're going to get a equal toggle on the high and the low side. Okay, so let's take a look as to, once the code is done, let's take a look and see if that's correct. Okay, so it's basically saying timer 4 CCR4, it doesn't matter, 200. Okay, must be less than ARR for equal toggle. Okay, all right, we want to set our thing to toggle. How do we set that up? Here it says select the output mode. For example, the user must write OCM011 for toggle. Okay, that's, well, where is that? Okay, let's go find out. Oops, where did I go? There you go. All right. We want the output mode. So OCM is in CCMR register. We want to write a 011 to toggle if the counter is equal to the CCR register. Okay. Similarly, we want a preload to be 0 in the CCMR. So in CCMR, we have two things to write to. Okay, we have two things to write to. A 011 on this to create the toggle and a 0 on the polarity. So let's take care of that first. It also says, let's see what the reset state is. Reset state is everything is zeroed out. So the only thing we should really focus on writing, we need to write, is the 11 here. Okay, so everything else is already 0. So where do we write a 1? We need to write a 1 on bit 13 and 1 on bit 12. Right, so timer 4 CC, this is the CCMR2 register, right? CCMR2 register, and we're writing to OC4M. Okay, we're writing to timer underscore CCMR2 into OC4M, and we want to write to bit 0 and bit 1 of that. So bit 0, and we want to also write a 1 to bit 1. So in other words, we can OR these two guys. Okay, right? And for the timer capture compare enable register, it says write a 1 on CC4E and a CC4P should be a 0. Okay, by default this is set to a 0, so we need to push a 1 on bit 12, which is CC4E bit. So we have timer 4 CCER register, timer 4 timer CCER, and we're looking at CC4E mask. Hopefully that, yep, CC4E mask. Okay, perfect. All right, and then finally, what else do we need to do? According to this procedure, after all of that, enable the counter by setting the CEN bit in the timer CR1 register. So in our case, timer 4 CR1 register, timer 4 CR1 register, we need to write a 1 in this bit. Okay, so let's go take a look and write just that. So timer 4 CR1 register, and we're writing to the timer CR1 count enable mask. Okay, so we basically enable count, and this was enable compare output 4. Okay, that's what that was about. Okay, all right, so I think we've followed all the procedure, and the last thing is while one. We don't need an interrupt service routine in this particular case, right? So let's build this, and hopefully there are no errors. Right, built it, no errors, 0 errors, 0 warnings. I'm going to download this to the board. You can either do the debug mode or you can flash and hit the reset button on the board. So let's run it. So I'm noticing that my blue LED on my board is beginning to flash a lot quicker. How do I show you that? All right, let's see. So right now there's nothing connected to the green, and the blue one is flashing really fast, so about a rate of half high, half low, I assume. So let's hit run. So this picture was from timer 6 and 7 earlier exercise. This time when I hit run, the green should just go low or high and not change. So I see the blue is changing up and down, equal amount. Blue changing equal amount. Okay, let's see. When I measure it, so high end is half a second, low end is half a second, half second, half second. Okay. All right, so it's having the desired effect that we were hoping to have. Now, one of the things I said earlier while we were doing this coding was, let me put the compiler right here, and this, I don't need timer 4 value right here. Okay, what I had said earlier was the CCR value, as long as it's lower than the ARR, doesn't matter. Okay, what this really does, the only thing this does is it tells you when the capture starts. So it tells you the original high, how long is high for. Okay, so let me do 480 here. Right, let's see. So right now this is the original one. Oh, I haven't loaded the code yet. So okay, I'm gonna stop this real quick. Okay, I'm gonna flash it so that I can hit reset and this button at the same time. See. Okay, I've flashed it. I'm gonna hit run, so nothing should happen on blue. When I hit reset, it should change. Okay, still seeing half. Okay, so this 499, or it can, oh sorry, this can be any value as long as it's less than ARR. So let me build again. Build again. I'm gonna load into the board and hit run. Nothing should be happening until I press the reset button, and that was the reset bounce. Okay, again, half on, half off. Okay, this is timers used as an output compare. Okay, that's what it means. We have 50% high, 50% low by setting this to a toggle mode. If we wanted to change this from toggle mode to other mode, what we would do is this value right here. This basically selects what mode we wanted to write, what mode we wanted. 011 was for toggle. 001, let's see what that does. 001 isn't for toggle, it was for 001 would be if set 1 if counter is equal to CCR. So it'll go low to high and stay high if I set that to 001. So let's go quickly change that and see if that is indeed the case. 001 means only the 0th bit needs to be a 1. So let me get rid of this real quick. Build this, and I'm going to load it to flash. What I should see in my here is I'm running it, nothing is happening. I'm going to reset it. It's going to go high and stay high. All right, there you go. When I reset it, it waited for the capture compare register to be equal to count, and after that, it stayed high forever. I see my blue light is constantly on, and you can see the logic analyzer as well that it's high. Okay, so I'm just going to stop there. Now, instead of that, I had so that was what I had just cut. If I switch from that to this 001, set 1, 010, set 0 if counter is equal to this. So you can do that under certain state. Or if you don't want to do anything on the output, but use the fact that the counter is equal to the capture compare register value that you set, you can set the output compare mode to 000. So nothing really happens at the output, but you can use that flag to direct an interrupt or do something useful with it with that particular knowledge. Okay, so that is basically the timer 4 used as an output compare.